Hello everyone, I am Sai Venkatrakrishnan, a PhD scholar from the Department of Computer Science and Engineering at IIT Madras. Welcome to week 10 live session for the NPTEL course Blockchain and its applications CS47. The agenda of the course would be, of this live session would be, is that if you have any queries in the um, current video lectures, in the current week's video lectures, or if you have um, any other queries in the previous video lectures, feel free to unmute yourself and ask those questions, or you can post the questions in the chat box. Okay. So now, as part of today's live session, I want to concentrate on a couple of things. So first one is managing wallets. Your Bitcoin wallet or the wallet software. The second thing is uh, how lightweight nodes in Bitcoin work. Okay, that is one. And the third thing is how Ethereum ghost algorithm works, right? So these are the three topics I'll be touching upon in today's live session. So starting with the first one, how what's the wallet software and how do we manage wallets, right? Oops, 1 second. So first, to understand this topic, first we should know the importance of wallet software, right? So if you take your example of Bitcoin, right, which follows the UTXO model, it is unspent. So this unspent transaction output, right? 1 second. Sorry. So the Bitcoin follows the UTXO model, where if you want to spend any transaction in any sort of the Bitcoin you own, if you want to send it to in some other account, you have to create a transaction where the input of the transaction specifies the previous transaction's output, right? It should specify to this transaction, and so this is how the UTXO model works. Okay, so in the same way, now if now in the Bitcoin UTXO model, you don't have one account address. There is no notion of an account address in Bitcoin. So there is no notion of account address in Bitcoin. All the addresses, whatever your transaction input refers to, is the transaction address, right? So in my previous live session, I have explained how the Bitcoin address is formed usually, right? The Bitcoin address. So the Bitcoin address is nothing but you take, uh, you perform a double hash, right, on your public key address, and that is your Bitcoin address. And uh, the private key which you use to encrypt, right? So the corresponding private key of this public key is the one which used to sign your transactions. And this double hash, this Bitcoin address, right? So this Bitcoin address would be part of your transaction output. Say like if Akshay wants to send some amount to Ganesh, right? So Ganesh's Bitcoin address would be part of this transaction. Okay, so if this transaction is semantic meaning is Akshay is sending some bitcoins to Ganesh, and Ganesh's public address would be keyed as part of the output, right? And if Ganesh wants to use this specific transaction, say this is transaction 1 and this is transaction 2, if Ganesh wants to use transaction 1's output, he has to sign transaction 2 using the corresponding private key. Okay, so say Ganesh is using a specific public key which starts with 0x CAFE, something like this, right? This is the public key which is encoded as part of the transaction 1's output. So in the transaction output you will have the set of conditions which are supposed to be satisfied whenever a transaction input refers to that output. Okay, so this specific public key is part of that constraint, and the corresponding private key should be used to sign the transaction 2 when you are referring to that unspent transaction output. Okay, and in Bitcoin usually everything is not in the smallest unit of currency in Bitcoin network is satoshis, right? So if I am correct, like one Bitcoin is around like 10 per 18 satoshis, something like that. Okay, not sure, but so around this range, right? 10 per 9 or 8, 10 per 18 satoshis. Okay, so everything is in terms of satoshis. So one Bitcoin, and when you have to, um, so when you are sending some transaction, say when you are spending some bitcoins, right? So since it's a UTXO model, everything is like every bitcoin is just nothing but a series of unspent series of transactions, which shows the order in which the money was created and sent to all the other sent to sent across the participants, right? So say like one Bitcoin initially a miner has. So miner one, he mined a new block and he was rewarded one Bitcoin. And now if he is sending that, if he is transferring that Bitcoin to another person, right, to some other account, say owned by, let's say, right. So this input refers to this previous transactions output. And the same way, if Akshay is sending to Ganesh, then this input refers to this output. right? So in the Bitcoin world, the Bitcoin as it is not like having any physical representation or even like a digital ID or something. If you have to get a notion of what a Bitcoin is in the digital representation, it's nothing but a series of transactions which uniquely identifies the spending trail of that specific coin. Okay, and in a similar way, how you perform financial transactions using your physical currency. The Bitcoin is also done in the same way, right? So, your any person, say like Akshay, he can have multiple, he can have like thousands of public keys or like the Bitcoin addresses he can generate easily, and these each Bitcoin address he can use in each transaction. Say like if Akshay has to receive some amount from like uh, 10 different persons, then Akshay can instead of sharing, so instead of sharing the same Bitcoin address, Akshay can create multiple Bitcoin addresses and share it with each participant, with each sender, right? The advantage with this is, unlike unlike a scenario where Akshay has a unique account number, like same way how your bank account number works, right? Instead of having like a unique account number, here Akshay is having like multiple Bitcoin addresses to which uh, all the 10 different persons would be sending some amount of Bitcoins to Akshay. The advantage with the second approach, right? So this is approach 1 and this is approach 2. Like Akshay is using either the same Bitcoin address to receive from 10 different persons, or is using different Bitcoin address for each of those transactions. The advantage with the second approach is it is more pseudonymous, more privacy, right? Because now say like some person was able to find out like Akshay is using Bitcoin address starting with 0x CAFE, some particular Bitcoin address. Some have found out that is Akshay's Bitcoin address. Now, if Akshay was using the same Bitcoin address everywhere, then since the blockchain ledger is open for everyone, right? You can use the blockchain explorer and etc. to find out in what all transactions a specific transaction address is being used, right? So using that kind of like an explorer and all those things, you can easily find out how much amount Akshay is having. You can find out the amount Akshay has. You can find out where all he purchased, or where all he performed transactions, right? He sent or received money, received bitcoins, and all those things, right? And the idea and what can be done is leads to like if your public key address, if someone is able to associate your identity with a specific public key address, then all your financial transactions are in the open, right? And that is something like which you don't want to have, which you won't want to happen, because uh, which you won't like it because your financial transactions has to be private, and it should not be monitored by some third party entity, right? So for that reason, what Akshay can do is, instead of sticking with one specific Bitcoin address, right, he can use 10 different Bitcoin addresses, or for every transaction he can keep on generating different public key and private key pairs. So he can generate different, right, for like for each of the, say he does perform some 1,000 transactions, means for each of the 1,000 transactions he can generate a different public key private key pair, and for the first transaction he can use one public key, and to use that transaction output he has to use that corresponding private key. So say like Akshay, so Ganesh sends to Akshay some amount, and later Bhairav sends some amount to Akshay, right? And here he can specify like some public key, say public key 1, and here he can specify public key 2. But in order to use the specific amounts as part of this transaction, he should sign the new transaction with corresponding private key. Private key 1 and private key 2, right? In this way, what happens is, say for 100 different transactions or thousands of transactions, for each of these transactions, if he's not reusing his public keys, he's not reusing his Bitcoin address, whereas he's making the addresses unique, means it becomes difficult for any third party entity to track all these addresses. So now, like say we know that the Bitcoin address starting with 0x cafe something, some arbitrary set of integers, we are able to identify it as Akshay's. But since Akshay is now not using that same public key or the Bitcoin address, it becomes difficult for any third party entity to track all the addresses. To track all the addresses and associate those to Akshay, right? It can be done, but it becomes a bit difficult, and also you cannot do that very easily. You have to sort of then traverse the whole blockchain and find out any relationship, right? So it is not like completely foolproof, but it's like a hindrance, and it increases the difficulty level to track all the addresses and associate those to Akshay, right? And usually, like when is the case, where is the case, a case where like people have to generate different addresses, which is like commonly used to say Akshay is sending some amount to uh, say Krishna, right? Akshay is sending some amount. Akshay currently is referring to a previous transaction, transaction 1, which has 10 bitcoins, right? But Akshay has to send just 7 bitcoins to Krishna, right? So for that, he will create a transaction where the input will refer to the previous 10 bitcoins transaction 1, but the output will have two different outputs. One would be referring to Krishna's Bitcoin address, right? And the amount is 7 bitcoins. And the second output would be to Akshay controlled Bitcoin address, where the remaining 3 bitcoins would be there. Not exactly 3. Uh, say like some 1 bitcoin goes for like transaction fee or something, zero point 0.5 bitcoin, right? So in that case, 2.5 bitcoins Akshay is like the change he gets out from this transaction, right? And usually these specific the addresses, so here Krishna's Bitcoin address will be included, right? But here in Akshay, within the second output, so this is 0, output index 0, and this is output index 1. So in output index 1, the address that would be included is what is called as a change address, right? And in frequently, if you are performing Bitcoin transactions, these type of change outputs would be very common, and it would be so frequent, where instead of you like manually initiating the public private key preparation and all those things, you will be using a sort of software called as wallet software. The wallet software is nothing but it has a couple of tasks, main tasks. One, it should manage your private public key pairs. Second, it should sync up with the blockchain, right? So this is the second task of like a wallet software. So it should sync with the blockchain to find out if the transaction is successful or not, and based on it, it should reflect the output status, right? And the third task is so, so suppose these kind of transactions, right? Like you have to send 7 bitcoins, but the least transaction output that you are having is 10 bitcoins, right? So say you want to send 7 bitcoins. Akshay wants to send 7 bitcoins to Krishna, and currently Akshay owns 5 different transaction outputs. Say he owns 8 bitcoins as one output, 10 bitcoins as the other, uh, 9 and 7.5, something like this, right? So out of these 4 transaction outputs that Akshay is holding, Akshay is the owner of, which output should Akshay use to send transfer 7 bitcoins to Krishna? So say suppose like if Akshay wants is using this specific 8 bitcoin transaction output, means the change what he would be getting is like zero point 0.5 bitcoins. Whereas if he's using this 10 bitcoins, he gets like 3 bitcoins as the change. And if he's using 9 bitcoins, it's like 2 bitcoins as change. And now um, the wallet, so there is a standard problem in computer science called as like the coin selection problem, right? Where say you have to what's the uh, minimum number of different coin currencies which you can use to in order to um, satisfy a condition. So say like you have a 10 1 rupee coin and 10 2 rupee coin, right? And 5 10 rupees, something like this, right? And finally, like um, the goal of the coin selection problem is your change should be minimized, like exactly to that specific amount. So say like you have to pay 5 rupees, rupees 5 to some person, rupees 7 to some person, and rupees 8 to someone else, right? So how will you split up these 10 1 rupees or 10 2 rupees and 5 10 rupees among these three persons such that everyone gets exactly the appropriate amount, but also in the least number of coins, and there shouldn't be like a change transfer happening or something like that, right? So that is basically a coin selection problem, and it's difficult to arrive at an optimal solution. You should use some heuristics and all those things to arrive at an solution. So your wallet address will usually be using some sort of simple algorithm, right, to find out which specific transaction output it should be using when you want to create a new transaction. So say uh, the problem what arises if say now if I am having 10 Bitcoin, if I'm using the 10 Bitcoin output, I get a change address of 3 Bitcoin, which is a significant amount, and most probably that 3 Bitcoins as a whole I'd be willing to send to some other person in a later transaction. But if I'm using the 7.5 Bitcoin output to specify the 7 Bitcoin Akshay to Krishna's transaction, I'll be getting a change of zero point 0.5 Bitcoin. And if I keep on blindly using this sort of strategy where the least amount which satisfies that transaction, which satisfies this transaction uh, input constraint, right? So what I'll be finally um, having is I'll be having like a set of transaction outputs around like 100 transaction outputs, and each transaction output would be like sort of having the change address, which is like zero point 0.5 Bitcoin, zero point 0.2 Bitcoin, like that, and all these put together would be amounting to some 10 Bitcoins, right? And now if this is the only amount I'm left with, and if I want to send this whole 10 Bitcoins to someone else, or if I would just want to accumulate all these 10 Bitcoins, right? And what happens is you should add all these change transaction outputs as part of your input, right? You should add it all as part of a new transaction input, refer to those unspent transaction output and create a new transaction. The disadvantage with this approach is you increase your validation time, right? So if you are using multiple inputs, then for each of the input you should go and check in the unspent the UTXO set whether the transaction is indeed owned by you and whether the output script matches your input script, right? And all those things. So for the so that increases your validation time. So usually the wallet software should instead of having the naive approach of finding the least um, Bitcoin amount that satisfy the transaction input, it should sort of uh, have this um, heuristic in mind, heuristic in its algorithm before finding a transaction output and using it, referring it while creating a new transaction, right? So coming back to the wallet software, so mainly these are the three different tasks of wallet software. One, it should be managing all your public and private key pairs, right? And by managing, what I mean is, so all these, so usually when you want to, as a newbie, right, you will be using some third-party wallet or wallet software, right? You will be using some wallet software, and there are different types of wallet software. Some are like implemented as a mobile app. Some would be like some desktop application, right? And some are hardware wallets. Okay, desktop applications. and some would be like web based, which is like universal, as in you need not, it's not tied to a particular device or something. Okay, but the most secure of all these wallet software is the hardware wallet. So your wallet software should maintain both your public as well as the private key. So you should maintain both your public and private key. And what happens? Say if you are sending how do you start sending a transaction, right? So your wallet software would contain a list of unspent transaction outputs, right? So, so your wallet software will contain a list of UTXO addresses which are in its control. So as in the wallet software will have a set of public key and private key pairs, and all the UTXO addresses which are attached to this public key, the set of public key and private key pairs, the wallet will contain the list of all these UTXO addresses. It will maintain that internally. And say now Akshay is querying his wallet software. He's going into the UI. He's opening up the application, the wallet software application, and he presses on like send some amount to a specific Bitcoin address means. Now the wallet software should first step one find out UTXO having that amount, right? So this basically the this is basically like sort of the coin selection problem that we discussed, right? It should find out, say, if I want to send 10 bitcoins or something, it should try to find out 11 bitcoin UTXO, or it should, if it has like 5 bitcoin UTXO, then it should merge these two in the same transaction and spend it, right? So that is step one. Step two is then once it has create the transaction, and step 3 is you sign the transaction. Okay, and this step over here is the crucial one, because your this involves your private key, and your private key is the is, like a single entity which proves ownership over your UTXOs, right? Because UTXO is referring to a specific public key address, and how do you unlock that public key address? How do you provide proof that you own that public key address? Is by signing the transaction with the corresponding private key. So if your private key should be secure and should be known to only you. It should be a secret. It should be a secret. So um, managing your private key and keeping it a secret is essential, is a very important task for your wallet software. And out of these different types of, so once this signing the transaction is over, as part of step 4, the it propagates the transaction to the mining node. Right, so these are the 4 steps involved in when you want to create a new transaction and sign it and send it, right? And now coming back to the step 3, right, how the private key is handled. Usually a wallet software is a critical part in this wallet software is how it handles a private key. And in mobile application, desktop application or web-based application, the disadvantage is it is part of a large piece of software code, and like in these three things, right? In web-based and desktop, in all these three, the disadvantage is it usually uh, vulnerable to cyber uh, cyber attacks, right? The reason being, like, say, you might be having a wallet software installed in your in your mobile application, and later when you visit some website, right, or some spam email comes to your inbox, and you by mistake click that spam email inbox, then if your mobile application is having some wallet software, your mobile is having some wallet software, that specific spam, that email address, sorry, that spam email might be vulnerable, might be like a malicious mail, and it might execute some malicious scripts to get control of the wallet software installed on your mobile. And if it succeeds so, then it has control over all of your private keys. And once it has control of your private keys, there is no way you can um, revoke those private keys or change the public key addresses, because the fundamental notion of the blockchain is it should be append only and immutable, and uh, once a transaction output is tied to a specific public and private key pair, you cannot go and change it, and there is no way of the of for anyone to prove that you are indeed the owner of that private key. The private key is the only entity which proves your ownership of a set of UTXOs or a particular UTXO, and if you lose that private key, or if someone able to get a copy of that private key, then you cannot prove your ownership in a unique way, right? To avoid all these things only, there is but if it's better if you use these hardware wallets. So these hardware wallets are nothing but it's like completely isolated. So, for example, say now if you want to create a transaction, sign it, right? Step one and step two, the hardware wallet will have a corresponding software wallet application, which will have like a UI sort of user interface module where it will be finding out the UTXOs and interacting with the blockchain explorer and all those things. It will create the transaction using all the details that you have given, that is the destination address, your the amount that you want to send and all those things. But for signing the transaction alone, for step 3, it don't do it on your mobile phone or on your desktop system or laptop. Instead, it will send this transaction um, to a specific hardware device connected to your system via USB or via USB, something like that, and it will send that transaction to the hardware wallet, a specific device, which just contains a set of public and private key pairs, and it will have like all the code that is used within the hardware wallet will be secure, and it will be like verified so that no bugs are present, and importantly it will be completely isolated. So there won't be any sort of internet connection, the internet connection to the network from a hardware wallet. So there won't be any network connection, something like that. It will be completely isolated. And the advantage with this approach is your attack surface is considerably reduced. Your attack surface is completely considerably reduced, because now if an attacker, right, in the case of a mobile application or desktop application which directly handles your private key, the attacker can try to um, hack your system and gain access to those private keys by sending out, like, say if it's on a mobile application, he can try to send attack via like some spam email, or he can send out some text-based messages to your mobile phone number with some links embedded in it, or he can try to connect via Bluetooth, right? Or he can um, send some. He can try to redirect your the websites that you go and traverse across, that you traverse in your browser, right? You can try to enter your mobile system through any of the above means, right? And also your operating system, whatever software you are using, the Play Store, which manages all your applications, if that is compromised or something like that, then the attacker can easily gain access to your private keys. But whereas in a hardware wallet, it doesn't contain any sort of software modules related to network connection, or is uh, your general programming, your general all those unused modules, right, are all removed, and just the essential modules, the software modules, which are used to sign the transaction. So just what all the hardware wallet will contain as part of its code base is some encryption modules for signing the transaction, a small data structure to manage the public and private key pairs, and a USB interface code for securely interacting with the system when it is connected, right? So this much of code is alone is alone present in the hardware wallet, and by that what happens is it becomes really hard for the attacker to find any specific vulnerability in your hardware wallet and gain access to the private keys which are stored only on the hardware wallet. The hardware wallet will encrypt those private keys and store it within its memory device, and even when your transaction is sent to the hardware wallet, it will be signed, and the signed transaction will be sent back to the mobile or the laptop, your desktop system, and the private keys won't be sent back, right? Your private key will always reside in your hardware wallet, and by that it is ensured that the attacker, right, it's like it becomes very difficult for the attacker to gain access to those private keys. So these are the different types of wallet software, and for better security, all those things, hardware wallet is preferred. Okay, and so that is one aspect, right? And now, so say in step two, right, when your wallet software creates a transaction. So in this specific case, when Akshay is sending some 7 bitcoins to Krishna, they change bitcoins around like 2.5 bitcoins that Akshay will be receiving. To which address should those bitcoins should be sent? And that address should not be you wouldn't be the wallet software wouldn't be asking you to specify an address. Instead, automatically the wallet software will create a new public private key pair and generate the Bitcoin address from that public key, and it will internally store those addresses as a set of change addresses. And whenever you want to send some amount to some other person, all these addresses will also be included as part of your as part of the UTXOs that you own. Okay, so the wallet software is also tasked with creating new change addresses and managing all those things, right? And so that is one aspect of the wallets. Now coming to the most important thing, right? uh, what happens if you um, say damage your wallet? Say you are having like a hardware or software wallet, and by mistake you delete the entire wallet software, right? Then what happens is all your private keys are lost. So all your private keys are lost, and just having the public keys doesn't matter, because only if you are having your private keys you can spend those UTXOs. Without those private keys you cannot spend the UTXOs, and it will just be orphaned out, right? So if you are uh, so in this there are many cases in real world where people by mistake they had erased their hard drive or thrown their hard drive in garbage, which resulted in like loss of around 1 lakh bitcoins, right? Which amounts to like so many crores, like 100,000 bitcoins or 10,000 bitcoins, like that, and that amounts to like hundreds of millions of dollars. And so having a backup of your private keys is a must. But the thing is you cannot store it online in some Google Drive or something like that, because it can easily be leaked, or so, or you can try writing all the private keys in a paper. But the issue is, if you want to write it down in a paper, right, you might make a mistake while writing it down in a paper. And because if you take any public key, private key pair, it will say RSA encryption, right? The public key encryption, RSA. So it will be like some 2048 bits, and it will be like 0xA12, like that, some arbitrary bit sequence, and it is tough to memorize as well as tough to copy it correctly. And the scale at which you are doing transactions, if you are doing very often, the the number of change addresses that would be created by your wallet would be high, and each time you should be noting those private key, um, the private key completely, and there is a high chance that you might make a mistake while noting it down. So what the current wallet developers perform is something called as deterministic seeded wallet. The idea is like you would be asked to provide a particular seed, like a passphrase or something, okay, and there would be a specific public private key generator, and right, and when this seed or passphrase is provided to the public or private key generators, it will keep on so once you initialize, you create a generator and initialize that with a specific passphrase which is secret and known only to you. The public key or private key generator will emit a list of public keys emit a list of public private key pairs which can be which are deterministic. So by deterministic, what I mean is they are reproducible, right? So this passphrase can is just like one single passphrase, as in like a long sentence or something like that, and this can easily be backed up on a paper or something like that, right? And now if you lose your wallet software, or you delete your you destroy your hardware wallet, or you delete your wallet software, nothing matters, because when you buy a new wallet again of the same company or the same brand, right, if you provide this same passphrase, which is known only to you, to the public key private key generator, it will emit the list of public and private keys which it would generate when seeded with this specific passphrase, right? So usually, in the previous case, without this deterministic seeded wallet, uh, the public and private keys which were generated were random, and user had no control over what public or private what private key was generated, right? It will just try finding out uh, uh, try some random numbers. If it matches that RSA mathematical function and all those things, that will be termed as a private key, and will just use that. Whereas the disadvantage is now you won't be able to, if you lose all the device or something, you lose all your private keys and you won't be able to spend your UTXOs. Whereas in this deterministic seeded wallet, you just have to make sure you remember this passphrase alone completely correctly, and if you provide this passphrase to the public and private key generator, that will generate a set of public and private keys in a sequence. So say if I give a passphrase like uh, CS47 blockchain, that's the passphrase means. The public and private key generator will each time when you query that generator to create a new public and private key pair, it will generate uh, random uh, private and public key pairs, but the sequence in which the pairs are generated will be deterministic. As in, say, like the first one, it generates, the first time you query, it generates 0x cafe, something like that, as the public key, and 0x1234. And the second time is 0x CBDE, comma 0x 4565. Like these are like the public and private key pairs means. Now if you again initialize the generator again and give it the same passphrase CS47 blockchain, the same 0x cafe it will generate. So by this what happens is even if you lose your hardware wallet, if you know that specific generator software, and if that passphrase is secret and known only to you, then the set of public and private key pairs that are generated are not uh, would be random for others, but it won't be random to you, but it would be instead it would be deterministic. And this type of wallet software is currently mostly the well known, because it is easier for the user to also have a backup of one particular passphrase, and use that in times of emergency where where the user loses his hardware wallet or something like that. Okay, so that is what is known as deterministic seeded wallets. Okay, and so that is the whole idea of managing wallets and the different types of wallets. And the second topic that I want to touch upon is how lightweight nodes work in Bitcoin, right? So, any queries till now? Okay, so let me continue with the second topic, right? How lightweight nodes interact in the Bitcoin. So usually there are different types of nodes. There are different types of nodes in the Bitcoin network. One is the miner node, which solves the proof of work challenge and adds the transactions to a block, solves the proof of work challenge and all those the proof of work, and propagates the mined blocks and gets the rewards. The second type of nodes are the validative nodes, right? So these validator nodes are crucial because we just don't have to rely on the miner node, whereas the validator nodes are the ones uh, which are like majority of the nodes in a network should be the validator nodes because they have to validate all the transactions um, that are present, um, and like all the transactions, and see that double spending does not occur and all those things. Okay, so now starting with so this is validator nodes, but not all the nodes have resources, right, to be a minor node or a validator node, because for minor node they should have computational resources, which is very difficult. Like it's economically it's like a high investment, whereas so even for a validator node you have to have some considerable amount of storage resources in order to store the recent blocks of the blockchain, at least like 100 or 200 blocks in the blockchain. Store those locally, and then um, engage, communicate with the other nodes and validate all the transactions and all those things. And all those will increase your storage requirements as the blockchain keeps on increasing. You can do pruning and all those strategies, but eventually the storage requirements will be pretty high. So lightweight nodes, say if you are an enthusiastic Bitcoin user who wants to participate in the Bitcoin network, but uh, do not just want to perform some transaction, but do not want to be a validator or a miner node. There is something called as the SPV, like simplistic payment verification. So these are just SPV type of nodes, where you will be running a application in your say a mobile phone or in your desktop, and the SPV nodes, that particular software will communicate, will with a full node. So this minor and validator nodes fall under the full node category, as in they will store all the blocks in the blockchain and store all the transaction details. And these SPV nodes will communicate with the full nodes, right? And they'll communicate with the full nodes, and say so this SPV nodes will be part of your wallet software also. Like the wallet software might also be part of act as like a lightweight node actually, and they will communicate with the full nodes. Say Akshay is having lightweight node and the wallet software, and if the wallet software has to find out whatever transaction created and signed and sent it to the miner or validator nodes, whether it is successful and included in the blockchain, it should communicate with those miner node or validator node. And how the communication goes about is the SPV node will provide the Bitcoin address or the transaction address or say like the wallet software has to find out, say like if someone sends some amount to Ganesh, right? Sorry, someone sends some amount to Akshay or something like that, uh, to like a known public address of Akshay, which the wallet address knows. It should sync up with the blockchain to find out the latest balance of that specific public key address, right? So it should sync up with the Bitcoin's blockchain ledger periodically, right? It should periodically communicate with the full node and get the latest transactions in which Akshay was the uh, recipient, and update its list of UTXOs, and either add it or add to the list of UTXOs or delete some UTXOs that were spent, and it should periodically update it, the wallet software. And for this, it should communicate and sync with the blockchain, and for this, it will communicate with the full nodes. So, how will it communicate with the full nodes? It will be sending out, say, hey, these are the list of public key addresses. Can you just uh, transfer back any specific blocks or something like that, uh, in part of which transactions, part of those blocks has these uh, public key addresses or Bitcoin addresses. Then the full node will use up perform, like explore the blockchain, and if any blocks satisfy those conditions, right, the wallet software or the SPV node will send a list of public key addresses to the full node, and the full node will search the blockchain which are having transactions having those public key addresses, and will send those blocks back to the lightweight node. And now the wallet software will go through those blocks and find out um, the specific transactions, and now update its UTXO set and all those things. But the issue in this naive approach is there is a loss of privacy. Because now what happens is your say the wallet software, Akshay is using the wallet software, and if uh, the full node, if they are able to track the associate that specific wallet's IP address to Akshay, right, then they can be pretty sure that all the public key addresses that the wallet software is asking for updates is associated with Akshay only, and they can easily associate this, and there's like loss of privacy, and your whole um, idea of creating multiple public private key pairs to have better privacy and all those things is sort of lost, because now if an attacker is controlling that specific full node or validator node, which is pretty cheap for an attacker because he does not have to be a mining node, he just has to be a full node, and if the wallet software communicates with those full nodes, right, the attacker can do some sort of analysis, like region-wise analysis. He can try to trace back the IP address, or try to associate a specific user to that specific wallet's IP address and all those things, and find out the identity. And so there's like a loss of privacy. To prevent this, right, this is like an active area of research where current like one way is to use bloom filters, right? So so what you can do is, instead of sending out like a list of public keys, so instead of sending out a list of public keys to the full node, what the SPV node can do is it can create something as like a bloom filter, where the bloom filter is configured in such a way that if some set of uh, say like the full node will uh, uh, traverse will provide will input some, say like if it inputs a transaction 1 into the bloom filter, right, the output will either be a 0 or 1 based on some specific conditions, right. So here in the first case, the full node will explicitly check whether the Bitcoin address in the transaction output or the input is one of the list of public key addresses given to it by the SPV, the lightweight node. But in the second case, instead of performing an explicit comparison, it will just pass this transaction to the Bloom filter, and the Bloom filter will be sort of like will have a hidden encoded comparison, sort of some comparison happens within the Bloom filter, and what comparison is not revealed, right? What comparison it does actually would not be revealed, but only the output would be visible, and that will be either a 0 or 1. And all the transactions that are having a output of 1 would be sent back to your lightweight node. And now the SPV node, what it does is it will create a bloom filter and configure it in such a way that not only with its explicit list of public keys, right, it will just also add some garbage public keys also, like some unknown public keys, like dummy public keys, something like that, and it will try to confuse, right. The main aim is it will confuse the full node. So initially, like the attacker control full node. Say uh, if I just ask for a list of transactions having public key addresses like 0x cafe or 0x dead, something like that, then it's very easy for the attacker to trace these public key addresses. But in a Bloom filter, you add extra conditions and make it like less accurate, and in a way what happens is a huge number of transactions would be satisfying, like a moderate number of transactions would be satisfying this Bloom filter condition, and the attacker would not be having the exact set of constraints or the exact list of public key addresses, but you would be having like a bloated set or a bloated condition, and there wouldn't be like there would be like slight privacy loss, but not compared to the first technique where you explicitly send out all your public key addresses. But now a small disadvantage is now whatever the lightweight node receives, right? If it receives like say in the first case when it sends out an explicit list, it will receive 100 transactions means. In the second case, since more number of transactions will have that condition true, because the condition of the Bloom filter conditions were set in such a way in order to confuse the full node. We add some extra conditions like unwanted conditions just to confuse the full node. So more number of transactions would be satisfying those conditions, and say in the first case it was like 100 means, now in the second case 1000 transactions would be returned back to the lightweight node, and now the lightweight node out of those 1000 transactions should select only the 100 specific transactions which it wants to which is actually related to its actual set of public keys, and remove all the other 900 transactions, right. So in this way, like you have to make a balance between how much information you want to reveal to the full node about your user or the set of public key addresses you are having, versus the number of dummy transactions or the garbage transactions that you should filter out when the full node sends it back to the lightweight node, right. So this is sort of a trade-off, and there are other advanced techniques to communicate with the full node without losing your privacy, like as in like minimal um, information is released to the full node and not the whole set of public keys and all those things, right? So this is what like a privacy concern when lightweight nodes interact with your full nodes in the Bitcoin network. And right. And coming to the storage requirements, right? So I mentioned a term called pruning. So usually, like now, if you consider your blockchain, right, it's been like around like 10 to 11 years since Bitcoin has been um, running, right? Has been up, and it has like lots of blocks now, and um, not all the full nodes would be storing the entire blockchain. So not all the full nodes would be storing the entire blockchain. So instead, only like few nodes, like out of their interest, say if it's like a company having substantial investment in bitcoins and all those things, those companies or those organizations, those nodes would be storing the entire blockchain in its entirety. Whereas in order to have like faster validation time and all those things, right? The initial only the recent 100 to 1000 blocks would be stored along with the UTXO set, right? Along with the UTXO set, only these recent blocks would be stored, and the remaining, the older history of the blockchain would be pruned off. But not all the, there should be few nodes um storing the entire blockchain, because like if some new node wants to enter a block, become like a full node, right? They have to download this. They have to bootstrap the blockchain, and like they have to download the blockchain up to the current block height and validate all the transactions, and then continue with the validation and all those things, right? So any like new node wants to enter the network, for those new nodes, some nodes have to be still holding all the blocks, the entire blockchain, to cater to those new node requirements. And for that, usually those specific nodes would be catering to those demands. But the remaining nodes which are doing actual validation and all those things, they would be sort of pruning away all the older blocks in order to make up space for the new blocks, and increase reduce the storage requirements and all those things. Right. So any queries you have till now? So in this video lecture, in this live session, we discussed about the wallet software, and we discussed how uh, the security of wallets, the main functionality of a wallet software, and what are the different types of wallet software, and why hardware wallet is more secure when compared to the other type of wallets. And the second thing we discussed about is how lightweight nodes interact with the full nodes in a Bitcoin network, and how um, privacy is of concern during this interaction between a lightweight node and a full node, right? So about how Ethereum is different from Bitcoin, we had discussed in yesterday's live session lecture in week 9, in the previous week's lecture. So I uh, so I guess these are all the things that I wanted to discuss with you. So thank you, and have a wonderful day. See you in the next week's live session.